Let's continue our discussion on electric charges. And note the use of the plural. Charges, plural. It is quite possible to have multiple charges interacting with each other. And that begs the question, what happens in that situation? And the answer is one kind of simple word called superposition. What does superposition mean? It means treat the effects separately and then be ready to add them up. The treat them separately part, well, you just do things one at a time, and we'll see examples of doing that. The add them up part, because of the vector nature of forces, that can be a bit painful. Let's take a look. Here is a Cartesian coordinate system, and within the region are placed three charges. One of them is negative 2.51 microcoulombs, another is 762 nanocoulombs, and the third is 8.54 microcoulombs. And the Cartesian coordinates of each are given. And you can see in the picture where they've been drawn, with the negative charge being drawn in blue. I recommend, in circumstances like this, that you sketch out a little picture and try and make it at least a little bit accurate. It's not necessarily having to measure things out down to nearest millimeter, but it is a good idea to make things at least roughly proportional. So, for instance, the third charge has an x component of 9.1 and a y component of negative 2.2, and so, yes, that's going to be in quadrant 4. But notice that the magnitude of the x component is more than 4 times greater than the magnitude of the y component. And what that consequently means is that the charge is decidedly closer to the x-axis than it is to the y-axis. So try and keep all of these in mind. And then let's consider the question, what is the net force acting on the negative charge? The negative charge, as I said, is the one that's in blue. Each of those two positive charges exert a force on the negative charge. Now, yes, those positive charges also exert a force on each other. I don't care. I am not looking for the force on charge 2. I'm not looking for the force on charge 3. I'm only looking for the force on charge 1. Well, that means that I look at the effect of charge 2 on charge 1, and I look at the effect of charge 3 on charge 1. And that's the idea behind superposition, where you treat things separately. Let's start doing that. The separation between charges 1 and 2 is going to be, from the distance formula, 12.5 centimeters or 0.125 meters. And through the distance formula, you should also be able to show that the separation between charges 1 and 3 is 0.152 meters. And that's going to be important because we're going to apply Coulomb's law, which we discussed in the previous lecture, to determine the magnitude of the force that charge 2 exerts on charge 1 and the magnitude of the force that charge 3 exerts on charge 1. The magnitude of the force that charge 1 exerts on charge 2, we do K times Q1 times Q2 over S112 squared. And you plug in the numbers that we have, and the magnitude of that force is 1.10 newtons. Because the charges are opposite to each other, charge 1 is negative, charge 2 is positive, that will tell us that the force on charge 1 due to charge 2 is directed towards charge 2. We can also calculate the magnitude of the force that charge 3 exerts on charge 1. Again, it's K times Q1 times Q3 divided by S13 squared. And since we're looking for the magnitude, we'll take the absolute value. And I calculated that to be 8.34 newtons. Again, we have opposite charges. So the force of charge 3 on charge 1, that force is going to be directed towards charge 3. So we've kind of done the first part of treat each thing separately, at least as far as the magnitudes are concerned. But the directions of these two forces are different, and we're going to have to worry about that. And we can take advantage, once again, of some basic trigonometry. The tangent of an angle is equal to opposite over adjacent. And in many circumstances, opposite is the difference in y, and adjacent is the difference in x. And in both cases, the force acting on charge 1 points to the other charge, and if we go back to the picture, we'll see that each of these forces, the force of charge 2 on charge 1 is pointing charge 2, so it has kind of an up, pointing towards the upper right vibe to it. And the force of charge 3 on charge 1, if I were to draw that force acting on charge 1, it would point towards charge 3, and it would also have a towards the upper right vibe to it. So both of those angles are going to be between 0 and 90 degrees. And in fact, I can pretty much say that the angle of the force of charge 2 on charge 1 will be greater than the angle of the force of charge 3 on charge 1. And that shows up in our numbers. The angle of charge 2 on charge 1, 47.6 degrees. The angle of the charge 3 on charge 1, 18.8 degrees. And this is where having a picture helps. We can see that the angle of the force of charge 2 on charge 1, it's not too far different from a 45-degree angle. And the angle for the force of charge 3 on charge 1 is not too different from about a 20-degree angle. So those numbers that we get here, 47.6 degrees and 18.8 degrees, I think do a pretty fair job of representing what those actual angles are. I have confidence in these numbers. Let's continue, because we've now determined the magnitude and direction of each of the separate forces. That's the first part of superposition. But now we have to add them up, and we have to take this vector nature into account. So we have to look at the x components of each force, and we have to look at the y components of each force. These angles, 47.6 degrees and 18.8 degrees, are measured with respect to the positive x-axis, so we can use cosine to get the x component and sine to get the y component. And then to get the net force, we add the separate x components together, and we add the separate y components together. So the net x component is 8.57 newtons, and the net y component is 3.44 newtons. Hopefully, this makes sense. If both forces, separate forces, are pointing in the direction of quadrant 1, we would expect the net force to be in the direction of quadrant 1. And if you were to graphically draw the net force, you should see that there's going to be a larger x component than y component. Let's talk about the word field. In Physics 140, you might have been exposed to the idea of the gravitational field. Isaac Newton thought of the idea of a field meaning that an object in one location has a field of influence that can affect an object at another location, even if they're not in direct contact with each other. So a field is a region of influence. There could be a gravitational field, there could be a magnetic field, there are other kinds of fields. We're going to talk about the electric field. So an electric field is created by an electric charge, just as a gravitational field is created by a mass. An important difference comes from the fact that charges have two possible signs. That's different from mass. Mass is always positive, and you always say the gravitational field due to a mass points towards that mass. Charges, because they could be either positive or negative, have situations where you would say the field points towards the charge, but they might have situations where the field points away from a charge. And that direction is determined, of course, by the sign of the charge, and convention holds that the electric field created by a positive charge points away from the positive charge. The electric field created by a negative charge points towards that negative charge. The direction was traditionally chosen because you imagine taking this charge and you just kind of nail it into place and it creates a field around it. But then you come along with a test charge, a movable test charge that will be influenced by the electric field in which it is placed. And this movable test charge is by convention treated as positive. So what would happen if I have a nailed in place positive charge and I came along and I placed a movable positive test charge in the vicinity? Well, that positive test charge would be repelled. It would move directly away from the positive charge. And so that's why the electric field of a positive charge points directly away from it. Similarly, if I have this negative charge and I take the nail and I pound it into place, and then I come along and I have this test charge in my hand and I place it in the vicinity of this negative charge, that positive test charge would be attracted towards that nailed in place negative charge. And so it would move towards the negative charge. And that's why by convention, an electric field direction is towards a negative charge. A few things to keep in mind. An electric field is a vector quantity. It has a magnitude and it has a direction. And because of the remarkable strength, the influence of charges, you can have an electric field of one magnitude and direction in one location, and then just a short distance over, the electric field could have a very different magnitude and a very different direction. That's something that we're not used to in our everyday experience. We live in a very close to uniform gravitational field, and that's how we kind of view the effect of fields. If I were to take a mass and I were to drop it in my house, and then if I were to take that same mass and I would drop it where you're viewing this right now, that mass would behave the same way. It would experience the same force. It would fall towards the ground. That's a uniform field. Electric fields could be uniform, but it is also exceedingly likely for them to be very non-uniform. So we have to throw some of our preconceptions out to take that into consideration. When electric fields are drawn, we'll find that the density of electric field lines can vary. And where the electric field lines are very dense, that indicates a region where the electric field strength is very strong. And just a reminder, the electric field represents the direction of a force that would exist on a positive test charge, an imaginary test charge if you want, placed at a particular location. What does that mean? Let's explore that a little bit further. And again, we're going to draw up our analogy with gravity. In Physics 140, I would bet dollars to cheap donuts that you saw the expression that the gravitational force near the surface of the Earth has a magnitude of m times little g, where m is the mass of the particle and little g is the gravitational acceleration. But I want you to think of little g as something else. Yes, little g is the strength of the gravitational acceleration and it has units of meters per second squared, but an equivalent set of units for little g is newtons per kilogram. Newtons per kilogram is a measure of field strength. You imagine taking a kilogram and placing it at a location where there's a gravitational field, and you would basically be able to determine the strength of the force on it. So how many newtons per kilogram? You know, you just take the number of kilograms, you multiply it by the newtons per kilogram, you got the newtons. It's a field strength. Yes, it's a gravitational acceleration, but it is a field strength. In electricity, we don't have mass, we have charge Q. And we're going to use a symbol for the electric field strength. So we're going to use capital E. And so if we draw up an analogy with the expression for gravity, F equals mg, instead of m we have Q, instead of g we have capital E. For electricity we have F equals QE. And that means that a charge placed in an external electric field will experience a force. Let's work with this. Suppose we have a 19.2 gram mass that also has a charge of 27.9 microcoulombs. And we place it in an electric field, and it has an acceleration of 59.1 meters per second squared, of magnitude of 59.1 meters per second squared. What's the strength of the field? Let's take a look at the information we're given. We're given massive acceleration, which sounds an awful lot like Physics 140. I don't want you to completely forget that stuff. That stuff still applies. And Newton's second law of motion is that the net force equals mass times acceleration. Now be careful about the mass. The mass is given in units of grams, and grams are not standard units. Kilograms are. So in kilograms, the mass is 0.0192. So 0.0192 kilograms times 59.1 meters per second squared gives us 1.135 newtons for the magnitude of the net force. If that net force is solely due to the electric field, then we can use F equals QE and solve for E. With a little bit of algebra, we find that the electric field is going to be equal to F over Q. I gotta be careful how I pronounce that, huh? And we plug in the number that we just determined for F. We plug in the number given for Q. Note that it is converted to coulombs, so it's 27.9 times 10 to the negative 6 coulombs. And if I did my number crunching correctly, we get a value of 40,700. And the units for the electric field are newtons per coulomb, which is just like units for the gravitational field being newtons per kilogram. It's newtons per relevant property. In gravity, the relevant property is the kilogram. In electricity, the relevant property is the coulomb. How do we determine electric fields? Well, we have two equations that can apply to point charges. One of them, F equals QE, applies to all situations. The other one applies specifically to point charges, and I'm talking about Coulomb's law. F equals K times Q1 times Q2 divided by S squared. Imagine one of those charges being kind of fixed in place, and it's the other charge that we come along and we place in the electric field of that first fixed charge. If we play around with the two equations a little bit, what we find is that that fixed point charge has an electric field that can be calculated as K times Q over S squared. K, of course, is the electrostatic constant of the universe. Q is the value of that fixed point charge. And S is simply how far away you are from that charge. Let's say you are in the neighborhood, as it says, of a 619 nanocoulomb point charge. Presumably this is positive. If it were negative, we would have to explicitly say it's negative. And like any good citizen, you have an electric field sensor on you. And you happen to take a look at the reading on that sensor, and you see a measurement of 158 newtons per coulomb. How far away is that charge from you? So the information that we're given, the electric field strength is given as 158 newtons per coulomb, and the charge itself in standard units is 619 times 10 to the negative 9 coulombs. And how far away from the charge are you? That's basically saying, hey, what's S equal to? So let's solve for S. A little bit of algebra says that S squared is equal to K times Q over E, and we can plug in those numbers, and we get that S squared is equal to 35.2. S is what we're looking for, though, so we have to take the square root. The square root of 35.2 is 5.93, and since everything has been in units of standard units, I presume that my value for S is also in standard units of meters. So I want to point out that that's a pretty small sounding charge, nanocoulombs times 10 to the negative 9, and you're almost 6 meters away from it. You're close to 20 feet away from it, and yet you're still detecting over 150 newtons per coulomb for an electric field. What is a reasonable value for an electric field? It is not unreasonable to see electric field strengths of hundreds of newtons per coulomb, thousands, tens of thousands, hundreds of thousands, perhaps even millions of newtons per coulomb. Not really that unreasonable at all. Okay. Given how this lecture started, you might not want to contemplate this, but what if we had to look at the electric field at a location in a region where there are multiple charges? Once again, superposition is going to come into play. And once again, because of the vector nature of the electric field, it has both a magnitude and a direction. It's going to be a little bit painful, a little bit long-winded, but hopefully you'll find it kind of straightforward. Let's consider the following question. The net electric field at a point of negative 1.5 and 2.7, and you'll see that the last sentence in black says assume all measurements are in units of meters, so in standard units. So net electric field at a point negative 1.5 and 2.7. There's no charge at that location, but we happen to be close to some charges. One of those charges is negative 9.13 microcoulombs, and it's located at x equals 2.5, y equals negative 3.7. And the other charge is positive 2.11 microcoulombs, and it's at a location of negative 2.3 meters and negative 1.1 meters. Okay, superposition applies, so we treat each charge separately. We are at this location, negative 1.5, 2.7. There's no charge there, but we are close to two charges, and so we are going to sense their effect in the form of an electric field. We'll first determine the electric field of charge 1, then we'll determine the electric field of charge 2, and then we will appropriately add them together. In order to determine those electric fields, we need to determine how far away we are from each charge. We are 7.55 meters away from the first charge, and we are 3.88 meters away from the second charge. Again, just using the distance formula to find these separations. We can now determine the strength of each field. It goes as K times Q1, the first one is K times Q1 over S1 squared. We plug in our numbers, we get 1,440 newtons per coulomb. We do the same thing for the second charge, and we get 1,260 newtons per coulomb for the electric field strength. But that's the strength. We also have to determine, of course, the direction. Again, we got to use some trigonometry and inverse tangent to do all of that. So the first angle, the inverse tangent of the difference in y divided by the difference in x, and I get negative 58 degrees. For the second one, difference in y divided by the difference in x, and I get 78.1 degrees. Now, these are what my calculators say, should I trust my calculator? Never trust your calculator when you are taking inverse tangent. Verify. Let's draw a picture of what's going on. The two charges are drawn. You can see that the red spot, which is in quadrant 3, represents the location of the positive 2.11 microcoulomb charge. And the blue spot in quadrant 4 represents the location of the negative 1.3 microcoulomb charge. The X in that picture represents where we are standing. There's no charge there, but we're close to these other two charges. If it's just the charge in red, that's a positive charge, the electric field that I would sense is pointing directly away from that charge, and so it would be represented by the red arrow. If the only charge is the negative charge, which is the blue spot, and I'm standing at that X, the only electric field that I sense would be pointing directly towards that negative charge, and it's represented by the blue arrow. Now that red arrow, it does look to be in quadrant 1. It looks to be between 0 and 90 degrees, and I'm okay with that. The blue arrow is between 270 degrees and 360 degrees, but alternatively, it's also between 0 degrees and negative 90 degrees. Negative 58 degrees does happen to be between 0 and negative 90. And so I'm convinced that these are correct. However, suppose that that blue spot, which, we're saying is a negative charge, but in the problem, it could have very easily have been a positive charge. And if it had been a positive charge, then the blue arrow would be pointing away from it. It would be pointing towards the upper left. And the funny thing is, the number on my calculator would still be negative 58 degrees, because calculators, when it comes to inverse tangent, can be extremely dumb. If you see a 180-degree discrepancy between your drawing and the number on the calculator, make sure your drawing is correct. Make sure you crunched the number on your calculator correctly, and then trust your drawing. Take the number on the calculator and add 180 degrees. I don't need to do that here. I think my angles agree with my drawing, but it's something you have to worry about in these situations. So I'm okay with these angles. Let's continue. I can calculate the X component of each electric field. I can calculate the Y component of each electric field. Since my angles are measured with respect to the positive x-axis, I can use cosine for x, sine for y. All is right with the world. And then to get the net field, I add the separate x components together, and I add the separate y components together. Let's move on. A very commonly occurring situation, and I alluded to this in the previous lecture, is that of what is called an electric dipole. Two equal but opposite charges in close proximity to each other. And field lines point away from a positive charge and towards a negative charge. If the charges are equal in magnitude, as they are in a dipole, the number of field lines associated with the positive charge will be the same as the number of field lines associated with the negative charge. So you can imagine each line from the positive charge terminating on the negative charge, and each line that terminates on the negative charge must have emanated from the positive charge. But in order to better understand this shape, I want to imagine the positive charge, which is represented by the red circle, as a mountain, and the negative charge represented by the blue circle as an undersea valley. And imagine that you have this mountain peak and this undersea valley. The mountain peak is as high as the undersea valley is deep. And let's say the sides are smooth, and you place a rock at some location. The rock is going to, if you place it near the top of the mountain peak, it's going to more or less start moving directly away from the mountain peak. And if you place it close to the bottom of the undersea valley, it's going to move more or less directly towards the undersea valley. But if you place it at some other location, the direction of the force acting on it is going to be somewhat away from the positive charge and somewhat towards the negative charge. And what you wind up getting is a set of field lines, much like what you see on the screen here. I hope that helps you visualize a little bit about what's going on. So this is just confirming it. Notice that I've drawn arrows on these field lines. Even the field lines that start off a positive charge and have an initial motion towards the left. Remember, we're talking about only this mountain peak and only this valley. And even if we place that rock far away from the mountain peak, unless it's literally directly on the opposite side of the mountain peak, at some point in time, it's going to curve around and want to reach the bottom of the valley. In the previous lecture, we considered different materials, conductors and insulators and semiconductors. I want to discuss something about conductors. And we know that conductors have all sorts of charges in them, and it is possible to place excess charge on them. The thing about them is if I place excess positive charge on the conductor, those positive charges want to get as far away from each other as possible. This is especially true on a spherical conductor. They are going to distribute themselves uniformly over the surface of a sphere. And the same thing would happen if I had placed excess negative charge. Like repels like, so all of those negative charges would try and move as far away from each other as possible. And they would accumulate on the surface of the sphere. And what that means is there is no excess charge inside the sphere. And that means that there's no electric field inside a conductor. All of the charges, all of the excess charges are on the surface. Any charges inside, there will be just as many tiny positive charges as tiny negative charges. They cancel each other out. The excess charge is on the surface. There's no excess charge inside. There's no electric field inside a conductor, provided the charges are stationary. Later this semester, we'll be looking at electric current through a conductor. We'll see that charges can exist inside a conductor, but they will be moving. If the charges are not allowed to move in a conductor, that means that they've distributed on the surface of the conductor, and there is no field inside the conductor. If you've ever seen or heard about something called a Faraday cage, that's basically the operating principle. The picture here is this is actually a time-lapse photo, and we didn't see all of these sparks, these bolts of lightning simultaneously. The individual inside the sphere, inside the cage, this cage is made of conducting material. It's made of metal. And so as long as this person inside isn't touching the metal, the charge that's built up by the device and is arcing across to the metal, and assuming that this metal is well grounded, the person inside is safe because the electric field inside the cage is zero. What about an insulator? An insulator, if you'll recall, charges do not move through an insulator. That doesn't mean that an insulator can't have charge, though. I can come along and I can inject a charge into a particular location in an insulator. And I can do that as many times as I want. And what happens is those charges stay there. So there will be an electric field inside the insulator because those charges, they're not moving. They're stuck there. That's about it for now. There will be more. Take care.